I think I lost audio again.
I can hear you, Steve.
Oh, okay, cool. Yeah, Como usually does intros, right?
Yeah.
Gotcha.
Yep.
Should probably figure out how to share screen. There we go.
Yeah, and Steve, I'll enable that for you in just a moment.
Yep, just wanted to make sure I knew where the button was. Everything's like super tiny on this computer for some reason. I don't know why. Like Zoom doesn't play nice with Linux.
Okay, here we go. Hi, everyone. Welcome to Always Coding. This is our weekly Hacky Hour. I'm Komal Devjani, a developer advocate with alwaysAI, and I'm joined today by Steve Batos, who's the machine learning engineer at alwaysAI. So welcome, Steve.
Hello.
And as always, Lila Milani, who is the developer advocate and software engineer at alwaysAI. So today's topic is the difference between YOLO models and MobileNet SSD models. So Steve has a presentation prepared for us to highlight what are the main differences between these two models, and we're going to get to that shortly. Before we do, we're going to get started as always. So for those of you who are new, just please follow along with this piece of the presentation. It's really critical for you to get started with alwaysAI by downloading the CLI and signing up. So what I'm going to do is share my screen and navigate you through this process. So you want to go onto alwaysai.co. And if you've already signed up, go into your dashboard. If you're new, you want to sign up, confirm your email. And once you're in here, you will see the opportunity to train a model, create a project, try out a sample project. But as I've said before, the most critical thing you'll do is download the CLI. So you'd click install CLI, select your operating system, hit next, and click that big red button. And then what you want to do next is just create a new project. I've created a project for today. I just called it our Hacky Hour, HH. And it's pretty simple. It has the default MobileNet SSD model. And what we're going to do is just configure it. This is a great way to see if the installation process worked properly and you're able to use alwaysAI. So let's just navigate into my directory, hit configure. There's going to add the models, and I'm going to save it locally. And then you just want to follow the steps right here. So AI app install, and then we'll do AI app start. And as you can see, this is working. Thank you, Lila.
Nice.
And we're going to copy this and then enter this here. And as you can see, it can detect me, my TV monitor, which it thought it was a bus a couple minutes ago, but there we are. So at least it's pretty confident that I'm a person at 99%. And that's how you get the MobileNet SSD model working. So that's the MobileNet SSD model. And now Steve is going to highlight what is the difference between this model and the YOLO model. So Steve, you should have access to the sharing capability.
Let's see here, desktop. There we go. Okay, you should see me.
Yes.
Yep.
Awesome. All right, cool. Yeah, thanks, Komal. So that pretty much covers the intro, so we can dive right into it. So a lot of you are probably pretty familiar with MobileNet SSD and YOLO v3 and all of the variations of YOLO that we have on our model catalog. It's pretty timely that we're doing this now because we've been working hard to bring you the ability to retrain YOLO v3 on your custom data sets. V4 is also in the pipeline, but the real question that I think a lot of you might be asking is, okay, now that YOLO v3 is trainable and runnable, is there any purpose to using MobileNet at all? And short answer is yes, but we'll talk about, the strengths and weaknesses of both here. So probably the best way to get started is just a quick side-by-side of each. They're both one-stage models. That means that they handle the localization and the classification of the objects in the image at the same time. There's a big difference in the base models between YOLO v3 and MobileNet SSD. So the base model of YOLO v3 is darknet 53. For previous versions of YOLO, we had darknet 19 in there. And the base model for MobileNet SSD is, of course, MobileNet. That's actually quite a big difference. We'll discuss those later. If you're not really quite clear on the concept of what a base model versus a framework is, that's totally fine. We'll get there. Some special features that the base models have. Darknet 53, since it is a deeper model, has these things called residual layers. And what those allow you to do is pass information down the network, so you're not losing information as you get deeper and deeper. MobileNet SSD, however, its focus is to be quick and fast and not really need any kind of crazy GPU hardware to run. And for that reason, we use these things called depth-wise separable convolutions. The detection frameworks, these are the things that do the actual detecting of objects. For YOLO, it is, you guessed it, YOLO. And for MobileNet SSD, it's the SSD. It's a little bit confusing for YOLO because the name of the actual detection framework is the name of the whole model, whereas MobileNet SSD, it's very clearly MobileNet and then the SSD. But we'll clear that up too after we get through this. So the bounding box initialization for YOLO v3, this is using k-means, and for MobileNet, it's just handpicked. And what that means is, so whenever you're trying to actually find a detection in an image, you start with these default bounding boxes, right? So you can't just say, well, there's an object here and the box is somewhere, anywhere in the picture. You actually say there's an object here and then that's somewhere in, this array of boxes that I'm allowing. The way that YOLO does it with k-means, it'll run through your data set and kind of figure out how best to structure those boxes. Whereas with MobileNet SSD, it just kind of goes by default boxes that aren't actually suited to your data set necessarily. The detection for the objects is done with CNN layers for both models. And with YOLO v3, we use 3 layers to detect objects, whereas with MobileNet SSD, we use 6. And to clear up this concept of base model, detection framework, and then, what an actual model is, the base model is what you use to get the features. So if you were just doing image classification, you would only need a base model that just takes your image and says, this is what's in it in terms of, something that's understandable by the machine. And then your detection framework is something that is layered on top of that, that says, okay, in this image, given these features, we're going to look for these objects and they are located here. So when I say a model, I'm actually referring to a combination of a base model and a detection framework. And yeah, that all comes together to form the actual whole thing. They're kind of also, it's worth noting that they're swappable. So like if I have a YOLO detection framework, for example, I don't necessarily need to use darknet 53 as my base model for that. I could, if I wanted to, put MobileNet into the YOLO framework, but people typically don't do that. YOLO v3 or YOLO, any YOLO is typically the darknet plus the YOLO framework. So just to clear that up. A quick side-by-side on the base models, like I mentioned before, darknet 53 has the residual layers that allow it to get deeper. And you can see here what they kind of do in a nutshell. You've got information coming in, they go through your weights, and then they get transformed in some way, but you're still passing information along past those layers to allow it to be preserved. And what that handles is you run into a problem with these deeper networks called vanishing gradient, and that can just be information loss essentially. So by the time you get all the way through the network, there's nothing really meaningful there. This allows that information to just continue to trickle down. And then MobileNet v1, they've got these special depth-wise convolutions, and they're about 9 times faster than the standard convolutions that you'll see in most other networks. The cost is accuracy, but then again, the use case of MobileNet is to be quick. And by using MobileNet, you are aware of that, trade-off. And in some cases, it's just fine. So yeah, just to kind of wrap it up, darknet is deeper, mobilenet is more shallow. One emphasizes accuracy, the other emphasizes speed. And then the detection framework for the SSD. This is actually a comparison between the first version of YOLO and the standard SSD that we're used to. So here are the 6 layers that they pass in to the actual classification layer. So what this does is allow you to detect objects at 6 different scales. So you can imagine like, okay, large objects will probably be coming from this scale because this is where you actually get your pretty, crude features. And then as you continue down, these are where your smaller objects are detected. And what this does is just allow you to kind of have a lot of different scales to detect objects at instead of just saying, okay, one shot, we're just going to look for everything. Which is actually what YOLO v1 does. And that's why I wanted to show it here. So YOLO v1 and v2, no, just v1. They have these fully connected layers here, which actually do the detections. And they're not grabbing a bunch of different scales to look at objects. And if you look at the comparisons between the accuracy of YOLO v1, which has, it says YOLO customized architecture here, but like I talked about earlier, this is actually darknet 19, the more shallow version of darknet 53. If you look at the comparison between things like this, it's really not that different. Like you don't get that crazy boost in accuracy that you see from YOLO v3 compared to the MobileNet version of this. And it's also worth mentioning that this is the original SSD framework from the original paper, which uses VGG16 as the base model, which is a little bit more heavy than MobileNet. So the MobileNet SSDs that we're used to, they're not using VGG16. They emphasize the speed that you get from MobileNet. I think that covers it for there. Yeah.
So Steve, just to pause for a second, I believe Irene here has a question. So
sure.
Irene, I've unmuted you. So you're welcome to, well, I've given you the permission to chat, so you can unmute yourself if you'd like to ask your question.
Nope.
No?
I think we lost her.
Okay, so yeah, we have another question here. How would the layers of both models handle facial features, then select the feature of interest and extract more details?
How would they handle facial features? Well, they pretty much handle all features the same way, right? What you're really doing is breaking down the image into its like transformed version, so a vector or something like that. That's what the convolutions do. You apply a bunch of different filters that are learned to the image, and during training it kind of learns, okay, if I'm running faces through this model, it's going to learn the weights of the filters that are specific to faces, and it's a little bit of a black box to see what's going on. Like if you actually pick apart what's going on in these layers, it's not really interpretable to a person, but it'll learn to extract the features that are necessary to identify a face, for example, if you were looking at training it for a face, like a facial recognition model. Does that answer your question?
Maybe to elaborate on the question a little bit, I think the question was more referring to how would you extract like details of the face? So maybe if you wanted to just see the eyes of the face and like learn more about that, how would both of those models perform?
Yeah, so you would have to train, if you wanted to just look at the eyes, or if you wanted to just look at different features of the face, you would actually have to train the model, this type of model, on the different features of a face. If you want to use a key point detector, for example, that's a different story. That's something that is actually in our Edge IQ platform right now, I believe. That will actually get you like, this is a point where the eye is, this is a point where the nose is, this is a point where the mouth is. But something like this, you wouldn't be able to just look at the vector that it outputs and be like, oh, okay, these like whatever 8 float values correspond to the eyes. It's not really something that you could interpret that way, because you can see here, this is like what you end up with if you were just to pass in a face, for instance, right? And the model knew how to look at a face. For the SSD, you end up with a vector of 8,732 elements. So to be able to pick the elements out that correspond to the eyes is a little bit, I don't know if that would be doable. But what you could do is have a model that actually learns to look for eyes. And that way you would know that if you have a class called eyes, you would know that that vector, regardless of what the elements in the vector correspond to, actually are the features that this whole model has settled on as important for eyes. So, in a nutshell, you can't really, without assigning an actual class for the thing that you're interested in looking for, you can't look at this vector and pick out, you know, interesting subclass features kind of thing. It would be very difficult to do that. You could do like I believe they're called saliency maps. You could probably do something like that, and then it'll give you a heat map of the face and what's most interesting to the model about the face, and then dissect that a little bit. But as far as just like grabbing something trivially that corresponds to something that you might be interested in, like the model might not actually be interested in eyes at all, for example. So it's not really a simple solution. Does that make sense?
I think so. DP, you're welcome to elaborate on your question. But if you were to select between the two models, YOLO and MobileNet SSD, which one would you select?
I would try both. I mean, that's spoiler alert for the end of the presentation. Yeah, it's good to try both. MobileNet does surprisingly well in situations that you might, like, it's not always just a one-off, okay, I'm going to use YOLO because YOLO is more accurate. You kind of got to try both. For something like facial recognition, or like to find, okay, I want to look for eyes in a person's face. If it's like right up there and you can get a really clear view of the person's face, I mean, I don't imagine that YOLO would have too much trouble at all finding eyes or, you know, a mouth or noses or anything like that. If it's like something farther away with weird angles and stuff like that, then I'd probably be more inclined to think about YOLO because it seems to do better in those environments. But I mean, the best thing to do is to kind of just try both. I mean, they'll be available in our platform, and it's really easy to just go through and, you know, give both a shot and see how they do. So, I mean, whenever I'm doing something on my own, I usually start with MobileNet and then climb up to YOLO as needed, because it's not really a big time investment to just try the MobileNet SSD and then build up from there if it's not quite meeting your needs.
Yeah. So this is a great follow-up question. How would you benchmark both models against each other?
Well, I would look at the MAPs that you're getting from both models on the exact same data set. So do your training validation split, keep that constant for both models, train both models on that data set, and just kind of do a survey of your MAPs. And I wouldn't actually suggest keeping the epochs or the steps the same for both, because, for instance, YOLO has a lot of parameters, MobileNet doesn't. I would just train until you reach the point where you're not improving anymore for either, and then kind of see where things top off in terms of MAP and MAP for both models.
What's an MAP?
But MAP is mean average precision. There's also average recall as well. So if you're familiar with the training toolkit and the output that you get every time it does a validation, those, like, I think they're like 12 separate lines. Those will give you your average precision and average recall at various IOU thresholds. And this is kind of a rabbit hole to go down, like that whole COCO evaluation metric, which is what you see there. There's a little bit of nuance to reading them, but basically bigger numbers are better. And what I usually look at is, I think the first element is average precision at an IOU threshold of 0.5. And that's, if you compare both of those for each model as you're training, you get a pretty good sense of like how they compare to each other. And then there's also recall, which is a trade-off between, you know, that's like the yin yang, I guess, is precision and recall of your training or model accuracy. So it's kind of like a balance and trade-off between the two. But I usually just pay attention to precision and just compare those two things for each model. If you want to compare, and again, this is assuming that you're familiar with the output that you get during training. If not, we can maybe go into that if we have time, but if not, like, we can chat on Discord to go deeper into this. But yeah, in a nutshell, that's probably how you compare. Just look at the outputs that you get for each evaluation on the model as you're training. And then when you're finished training for both, compare the numbers, see what is higher, and that's your better performing model. But it's also good to just pull it into a starter app and run it on whatever validation set you might be looking at. Like, I mean, even though the numbers are higher, it might be like, okay, well, I don't really need this kind of accuracy in this particular use case. MobileNet's good enough, and it allows me to run faster and on cheaper hardware. So that would be the choice. It's really, there's a lot of variables at play. It depends on your use case to convolute it a little bit.
So yeah, I'd actually like to go into that if you do have some time later on in the presentation.
Yeah, sure. We can get there. I'll kind of show you what I mean. I might have a file kicking around somewhere so that I don't have to spin up training, because I've got like a development version of it right now on my laptop. But if there's time, absolutely, we can look into that.
Perfect.
But yeah, let's get through this first. Let's unless there's other questions.
Yeah, there's a couple other questions. So
Okay.
are the frames per second specified at the same input resolution?
No, I believe for the SSD, the default is 300 by 300. And for YOLO, the default is, I think, 416 by 416, but you can dial that down to 320 by 320 if you want to, and then kind of get a, we'll do that later in the, I can compare the frames per second easily. I've got that set up and ready to go, but we'll, yeah, the resolution isn't the same. It can be close, but not the same.
Perfect. And the frames per second between the two would be similar across hardware? Well, not between each other, but across hardware. Would you say they have the same frames?
I'd say if your model is capable of running both, or if your hardware is capable of running both, like I don't imagine that your frame rate, for example, if I run on my laptop, I get maybe 4 FPS for YOLO and like real time 30 FPS for MobileNet. If I were to go to a Raspberry Pi or something like that, I probably would not get the same results under the same conditions here because the hardware is different. I'd probably get something similar for MobileNet, but YOLO would probably chug along quite slowly. I've never actually tried it, but I wouldn't bank on getting like a one-to-one translation between the two under the same conditions for different hardware.
Okay, cool. All right, let's keep going.
All right, cool. So now we're on to the YOLO v3 detection framework. One thing, I'd like to backtrack a little bit real quick because we took a bit of a divergence there. But so YOLO v1, pay attention to these fully connected layers here, and then notice that they're gone for YOLO v3. So YOLO v3 actually came after the SSD, and it used this idea of sampling at various scales in various feature resolutions, I guess. So this is, you know, what you would use to get your large, medium, small objects. SSD uses 6, YOLO only uses 3. And I haven't actually found a definitive like statement as to why YOLO can get away with detecting at only 3 layers, whereas SSD uses 6. But I would assume that it's because of the deeper Darknet 53 base model that it would use, thereby letting it extract features at a lot more, you know, granularity. But yeah, so the update to YOLO v3, the big update is that it's now detecting at 3 different scales of objects rather than just that one fully connected layer that's trying to do everything. And the benefit of this is you get a massive increase in your recall for only a small loss of your average precision. So that's a good thing. That means your model has more room to grow and kind of train and get more accurate in your precision side of things to even things out. Another quick tidbit is, see these upsample layers here? This is actually the reason why you need something that is a multiple of 32 for your YOLO input size. It's because of these upsampling steps here. So it's always going to upsample at a factor of 32. In order for that to work, you need a square image that's divisible by 32. So that's just something to keep in mind. And then we'll get into the numbers. So first off, we'll compare SSD 300 and YOLO v2. And keep in mind that SSD 300, like we saw earlier, the 300 doesn't matter. That's just the input size. But when this paper was written, it was using BGG as the base model backbone layer. And YOLO was using Darknet 19. So you might be a little bit shocked if you're used to comparing MobileNet v1 and YOLO v3 to see that the numbers are pretty much in line, right? And they are, because these are like earlier iterations. But the reason that I wanted to show this is to illustrate that just because a model is better on average doesn't mean that it's better for every class across the board. So you can see here, like horse, for instance, SSD wins in that category. Whereas if you look at person, YOLO is the winner. Then I think there was one here that was actually quite drastic, like sofa. If you're trying to detect a couch, go with the SSD, clearly. But yeah, that's really what I wanted to show here. So it's kind of getting back to the answer that I gave to the previous question asker there. You know, which model should I use? It's not always very clear, because some models might perform well with certain classes, whereas others might perform well with other classes. And it's not really like trivial to figure out which one would do best in which scenario. You've really got to try it both. Like this, everything about machine learning is an iterative process, and it's best to just kind of go along with it in that manner. So
Steve, that's actually so interesting. So this is my question. What determines which classes perform better with which models?
Yeah, it's tough to say. I mean, if you look at what a network is, right? Like a model, you've got millions and millions and millions of parameters, and it's very difficult to say, okay, this will do better for this class because of this, like, you know, fancy trick or whatever. What I do know is that it seems to be that the SSD is worse with small objects, whereas YOLO tends to do better with smaller objects. And I think, again, that's because of the deeper network, YOLO v3 specifically, because that's the one that uses the deeper network, right? That uses darknet 54. If you were to run YOLO v2, I would assume it would do just as poorly on small objects as MobileNet SSD. But YOLO v3, since it has a deeper network, right, it can presumably do better at extracting finer details. And I believe that that's what gives YOLO v3 its edge when it comes to detecting small objects over the SSD. So that's really the best rule of thumb that I can give, is that SSD, if you've got small objects, you might want to switch to something like YOLO, or you can even actually, like, a little trick is you can increase the image size on your SSD, and that's available in the model retraining tool. And that'll allow you to now turn small objects into bigger objects, right? Because it's talking the absolute pixel area that an object covers, not like relative to the image. So your small object, if it's, let's say, I don't know, 120 pixels squared or something like that in area, you can double your image size and turn that into something that's larger effectively. So that can kind of negate the issues that the SSD has with small objects. But yeah, that was kind of a roundabout answer for a pretty simple question. Yeah, it's not really easy to tell which is better. Like, I mean, what I would do is find charts like this and kind of think, okay, what's similar? Like, I'm trying to detect, I don't know, like coffee tables. And SSD says that it's better, according to these numbers, at detecting tables. So therefore, I can infer that my model for detecting coffee tables should probably be the SSD. But again, it's easy to try both. So that's kind of the route that I would go, is to try both and just see how well they perform.
Yeah.
Yeah. So
great.
So now we'll look at some more updated numbers here. This has YOLO v3 with the darknet framework, and this is comparing it with a few different models. So you can see, first of all, that YOLO v2 compared to YOLO v3 is, you know, significantly worse. YOLO v3 is a massive improvement in pretty much every area over YOLO v2. And that's actually mostly because of the darknet 53 architecture instead of the darknet 19 architecture. Actually, I highly recommend, if you're interested in computer vision, to read this chapter of this textbook. And the author, like, specifically says, yeah, basically the thing that's pushing computer vision forward is the ability to use deeper networks and the hardware that allows us to use deeper networks. And there are some tricks like residual layers that facilitate the use of these deeper networks. But yeah, that's kind of, if you're wondering where that massive jump came from, deeper network, extracting the features. And then we can compare with the SSD here. And this is, again, not using the MobileNet backbone. It's actually fairly tough to find charts that just compare YOLO v3 directly to the SSD with MobileNet as the backbone. But you can see here, this is the SSD 513, so a larger input size SSD with a far more accurate backbone than MobileNet is in terms of extracting its features, and it's still better. And then to go even further here, we'll look at some actual numbers on a chart, and the obvious choice among these contenders is YOLO v3 in pretty much every situation. But keep in mind that the SSDs that are used here are not the ones that we have in the catalog with MobileNet. MobileNet would be far quicker than what you're seeing here, and I'll show you that in a little bit after we get through the presentation. But this is just to kind of compare YOLO v3 with some other various networks. It kind of makes these ones obsolete and boils it down to like MobileNet versus YOLO v3. But what I do want to point out is that it depends on how you slice it. So you can see here, pay attention to this. This chart was taken at MAP 50. And what that means is this is looking at the mean average precision at only an IOU threshold of 0.5. So all you need to consider something, good or bad is a 50% overlap between the box that the model detects and the box that is actually bounding the object of interest. Whereas this MAP is taken at points from 0.5 IOU threshold all the way up to 0.95. So essentially, like in a nutshell, what this one is doing on the left here is scoring a model based on its ability to hold like a very tightly bound box around the object of interest. And what this is on the right, it's saying, we don't really care about the box being super accurate around the object necessarily bounding it, as long as it's actually capturing the object. And does it matter to go above 0.5? It's tough to say. I took a quote here. I didn't cite the paper because I couldn't actually find the one that had it. But if you're familiar with COCO, the data set and the evaluation metrics associated with it, one of the people that were developing the standard for evaluation of that said, I think it was, they ran a study and people couldn't actually tell the difference between an IOU of 0.3 versus an IOU of 0.5. So they couldn't really tell the difference between the two overlaps. And the rationale here was from the author of YOLO, and that paper was, if people can't actually tell the difference between 0.3 and 0.5, then does it really matter? Like, as long as the human eye can't actually detect those errors, and as long as the actual object of interest is bounded somewhat satisfactorily, does it matter? And it's really up to the person. If you need super accurate bounding boxes, then there are superior options here. Like, you can see that if you need like an IOU overlap that's almost perfect, you'd go with RetinaNet and whatever backbone they had here. You'd have to read the paper to figure that one out. But if you only care about like loosely bounding your objects, this is the score for YOLO at that point. So yeah, basically in a nutshell, YOLO is good at detecting the objects, but not necessarily tightly bounding them. Whereas some of these other models are better at coming up with a very, very tight bounding box that is exact to fit the object. Oh, it's demo time.
Steve, before the demo time, is RetinaNet for face detection?
I don't believe so. I haven't actually looked super deep into what the RetinaNet model is, but I don't think it's specifically for face detection. I'd have to get back to the question asker on that one on Discord. So feel free to ping me on there and we can talk about RetinaNet all day long. But that's actually a good question, and we can both learn something from it. So yeah, do feel free to reach out and we'll chat about that. But I don't think off the top of my head that it's specifically looking for faces. I know the name kind of suggests that, but I think there was some other clever reason that they called it RetinaNet.
Okay. And then we have another one here that says, why are the YOLO points out of axes?
Oh, yeah. Okay. That actually is kind of funny. On the paper, so it highly recommend that you read the YOLO v3 paper. The author was actually kind of funny when he wrote it. And it is a completely different tone to any other academic paper that I've read. They thought that it would be more, it would have a little bit more wow factor, I guess, if they just like said, look, it's off the charts in terms of inference time. There isn't really any reason besides just appearing as though like, yeah, look how like we're so far away from these clusters in terms of inference time and accuracy that we're like off the charts. That's really it. It was just a kind of a design decision on the author's part. No real purpose besides just to be silly. Okay, so let's check out the demos here. So what I've got prepared is a starter app. Hope you like purple. That has both models. So we've got MobileNet and we've got YOLO. And these are taken directly from our catalog. If you want to get these yourself, I'll just type it in here. You can do AI app, how do you spell, models, add, and then, either this or this to follow. So like, that's what it would look like. And then it would pull it down into your starter app, and then you can install it, and then you'd have, a similar environment to what I'm doing here. But we can talk about that later if you guys are having trouble getting set up. But anyway, what we want to do right now is just compare MobileNet and YOLO. So I've got 4 videos here. We'll start with people. And where do I have this? There we go. And I'll start this, and then we'll just watch it and see how it performs. Keep refreshing. Oh. So this is MobileNet. As you can see, not that fantastic, right? So if I wanted to build something in production that needed to really detect people accurately, this would not be it. But if I go ahead and switch to YOLO v3, we'll see. Where did I put it? Ah, there we go. Here we go like this. If I go ahead and switch to YOLO v3, check out how that does. There we go. That's much better, right? But it's also much slower. So that's the cost that you pay for these kind of things. It's actually quite a bit slower right now because I'm presenting. It's usually at around 5 frames per second, 4 frames per second. This is like 3. But what you lose in terms of speed, you gain in terms of accuracy. I hope you guys can see all the bounding boxes here. It's just doing fantastic. Maybe I can actually try something. So I mentioned earlier about how you can change the size. Yeah, okay. So let's try this. I'll show you how you can speed things up with YOLO. You're going to lose a bit of accuracy, but what I'm doing here is changing the input size of YOLO from 416 to 320. And if I rerun this app, it should be quicker. So I'll just cancel that. Let's see. Oh, I had it. There we go. Okay, yeah. So you shave off about 100 milliseconds there by changing the input size. And you don't really suffer in terms of the accuracy in this case. So if it were me, I'd say, well, let's get that boost of speed. We don't really need that large input size, and let's just dial it down to 320. And remember, it's got to be a multiple of 32. So 320 is about as low as I've seen people go in terms of the input size. But let's try another one. Let's look at MobileNet. And we'll see how it performs on vehicles now. And where did I put it? Here we go. Okay, so let's get that started. All right. So again, real time, but your detections aren't quite as accurate as you might want them to be. That's about, this is a half-hour video. We're not going to watch it all. So switch to YOLO v3 real quick. Bracket. probably already know what to expect here. Does well, but it's very slow. Okay, so you're probably thinking at this point, well, I mean, I'm never going to use MobileNet because it just, you know, as great as it is with speed, it just doesn't quite cut it in terms of accuracy. Well, that's not quite always the case. Let's look at this. And remember that SSDs, we saw that they did better with horses based on that table. So kind of arbitrary, but let's check it out. Okay, so here's the case where you get the speed and the accuracy from MobileNet. And I think that the reason that this is great is because, you know, it's a large object. It's kind of always in clear view. This is kind of a use case for MobileNet. You get the real-time benefit, and you also get accurate bounding boxes until it gets further away. And of course, that's because of the issue with small objects that it has. But I think this might come closer, and then we can see it again. I just ripped these from YouTube. I have no idea what they're even. Okay, yeah, see, so here's another case. Like, it's real time, blazing fast, and your bounding boxes are pretty correct. So, I mean, in this case, the choice would be obviously MobileNet, and I don't even think I have to show you YOLO, but I will. You'll think it's running like a snail. It's really slow. Let's see. Yeah, so here, I mean, kind of just as good as MobileNet, just much slower. So again, like, you can kind of use these rules of thumb, like, okay, the objects are like really large and clear and distinct. So MobileNet might be the case, or might be the thing to go with. But I mean, the best practice really is to just try both. Like, the emphasis that we wanted to put on model training and, you know, inferencing and everything with the product is you can experiment. It makes it really easy to do so. There's no reason to commit to a single model when it's as simple as a few clicks to just try both. That's it for the videos that I've got, but there's a little bit more of the presentation that I think I already covered. Yeah, so let's talk use cases. MobileNet SSD, it's quick to train, it's small, and it can run in real time on a CPU. So that opens up a ton of options in terms of hardware, makes it really portable, makes it quick to train, very easy to work with. Like, in general, if everything else was equal and the accuracy that YOLO had was capable with MobileNet, that would be the clear winner in any case. And again, like I said, it can be surprisingly accurate for objects that aren't too complex. Like, I've actually been quite shocked when it comes to, you know, the way that MobileNet can handle certain things. There were some cases where I'm thinking, you know, MobileNet's not going to do well here at all. And then I'll train it, and then I'll look at the results, and it's like, okay, well, you know, it actually does quite well. I don't need to move on and try YOLO v3. But YOLO v3 does have superior accuracy on average. It's just slower to train, larger. You can't be as lax in terms of hardware. So yeah, to conclude, start off with MobileNet, see how it does, check your results, either visually by pulling, you know, that model that you trained into a starter app and running it against some images, or just check the MAPs as they come up on your training logs. And if MobileNet doesn't cut it, then go ahead and move on to YOLO v3, and that should do it. You just got to consider that your hardware is now a little bit more restrictive with YOLO v3, and you won't get the like 30 FPS real time. And that's about it. That's all I've got. So I hope you guys enjoyed it, and I hope you learned something.
I really enjoyed it.
I learned something.
Yeah.
Yeah, I really enjoyed it.
Yeah. Does anyone have any other questions for Steve? You can raise your hand, write the questions. So yeah, Steve, okay. This question is, what about 60 FPS?
60 FPS. You might be able to get that with MobileNet. I haven't actually seen it because it's not actually too common of a use case. Usually 30 FPS is perfectly fine. But if you are, I don't know, actually, maybe, I don't know if Steve G or Tyga or any of those guys are in the webinar, but they'd be more apt to answering the acceleration of these models than I am, but I haven't seen 60 FPS before. But my inclination is that the only model that would be able to provide that for you, unless you're running on some crazy GPU rig, is the MobileNet SSD.
So yeah, Steve is on. Hey, Steve.
Yeah, that's true. What Steve just said there. You can do it on FPS, but you have to truly do it, you have to have a camera system that can actually support putting 60 frames per second into place to truly do it, right? So what I mean is most of us are going to find out that the camera is limited to 30 frames per second, and MobileNet can handle that fine. It'll get up, it obviously won't go 30 frames per second because there is work, but it'll get up high in the high 20s. Now, what I think some of you guys see on NVIDIA's pages running TensorRT and things like that, you'll see them go, oh, we're at 60 frames per second. What they're doing is they're processing the same frame over and over. So to get that, but you can achieve on the MobileNet SSD, version 1 for sure, and 2, 60 frames per second if you wanted to, on at least the Jetson Xavier. Hopefully that it makes sense to people.
Makes sense to me.
Yeah, DP, I said thanks. Great.
Yeah.
And then when will
but always be careful when you're watching some of the NVIDIA returns. I've seen them on stuff that they are multiply processing frames. That I've seen. So
great. And then when will model training for YOLO be available with alwaysAI?
Version 3, I'm assuming that you're asking about, right? Not version 4. I believe we're working hard on pushing that out by early next week, if not the end of this week.
Okay.
I'm a little bit messy with the schedule, but I think that's correct.
Great.
yeah, we'll make we're just debugging some of the stuff. We'll have a desktop release of 1.3, and we're hoping to have it out this week, but we've hit some error cases on the Windows platform. We should be getting that out about mid next week, and we'll announce it in Discord.
Sweet. All right. So yeah, we don't have any other questions, but we can keep going. You can ask any questions on Discord. I'll post the link in a minute. And yeah, it was really great to have all of you. Thank you so much for being part of the community, and we'll see you next week at Hacky Hour.
All right. Thanks, guys, for coming.
Yeah. Thanks, Steve, for joining.
Thanks, Steve.
Absolutely.
All right. Bye, guys.
See you later. So how do I exit now?
End meeting.
There it is. Leave. Tiny little button.